Good evening, C. I'm Mason, and I'll be your interviewer today. How are you feeling about the interview so far?
I'm feeling good. Everything's running smoothly. Let's keep it rolling.
Glad to hear it. I'll take us straight into the first problem. Tell me about a
First,
time you made progress when requirements or data were incomplete. Use a star-style answer and connect the lesson to an Amazon-scale engineering area, such as checkout.
there was a project where I had to design a monitoring system, but early data was sparse. I first outlined what was certain. We needed real-time vitals from devices. I then tested assumptions like which sensors worked reliably through small pilot deployments. As gaps closed, I iterated quickly. Connecting this to something like Amazon Checkout, when data isn't complete, you still ship, but with safeguards. For example, in Checkout, you might launch with A/B tests refined based on user flows and ensure fallback options so no customer is blocked.
Can you add the situation and action part to that? Walk me through it with Star.
The situation was that we had to build a health monitoring system, but early on we lacked reliable data from all sensors. The task was to create a stable system despite these gaps. The action I took was piloting the system with partial sensors, gathering data from real-world usage, and continuously adjusting the logic to handle uncertainties. The result was a system that improved as more data came in. The lesson, tied to Amazon scale engineering like checkout, is that you deploy iteratively, ensure critical paths have fallbacks, and refine based on actual user interactions.
Good thinking on that one. Moving on. Talk me through your reasoning as you go. The coding problem is now on your screen.
We want the sum of the chosen elements after flipping signs to match the target. First, we'd explore all possible sign combinations like a decision tree. For efficiency, we'd use backtracking or dynamic programming to avoid redundant checks. After finding valid sums, we'd choose the result lexigraphically, meaning the smallest in order. If no valid subset exists, we return an empty array. The plan is explore combinations, check sums, and pick the minimal ordered solution.
Before we move on, what's the time and space complexity of your approach, and briefly justify each?
Time complexity would be exponential, since we're essentially trying all combinations of sign flips, like 2 to the power of n. Space complexity, if we use a dynamic programming approach to track partial sums, would be proportional to the sum range we track, potentially a large but finite set. In short, it's exponential time due to combinations, and space depends on the tracked sums.
Right. You flag the exponential brute force, but the problem statement gave you a constraint, the sum parity check and the subset sum reduction. How does that change your approach? Walk me through the algorithm on a concrete example.
You're right, constraints matter. With the parity insight, we know the sum of flips must align with the target's parity. If that fails, no solution. Next, we reduce it to a subset sum problem. We aim for a certain difference between two subsets. We'd sum the entire array and figure out what difference yields the target. Then, using dynamic programming, we'd efficiently check which subset sums are possible. Finally, among valid solutions, we'd flip the minimal set of elements and choose the smallest in lexicographical order.
We'll park that. Here's the next. Design a practical Amazon personalized deals feed that can rank deals based on user interest, inventory, and business constraints. Cover requirements, APIs, data model, scaling strategy, reliability, and operational trade-offs. Talk me through your reasoning as you go.
We'd start with requirements. The feed must be real-time, personalized, and respect inventory. For APIs, we'd have a user deals endpoint that takes user preferences, recent behavior, and context. Our data model would include user interest vectors, deal metadata, and inventory status. For scaling, we'd use a distributed system, caching popular deals and pre-computing some rankings. For reliability, we'd ensure fallback deals if inventory data is stale, and we'd monitor latency closely. Operationally, trade-offs might be real-time complexity versus freshness. We might batch update inventories every few seconds to balance scale and accuracy.
You mentioned batching inventory updates every few seconds. What happens when a deal sells out mid-batch? Walk me through the failure mode and how you'd handle it.
If a deal sells out mid-batch, there's a risk a user sees it briefly when it's no longer available. To handle that, the moment we detect a purchase that could empty inventory, we'd flag it as pending. Any user request at that moment would get a fallback recommendation. If the batch catches up and confirms it's sold out, we seamlessly remove it. In short, we fail gracefully. No user clicks a deal that's gone.
Can you outline the high-level architecture and how the core components interact?
At a high level, we'd have a user profile service holding interest data, a deals engine ranking deals per user, and an inventory service tracking availability. The front end calls the Deals API, which queries user interests, filters deals by inventory, and ranks them. We'd use caching for common deals. The pipeline would be front end calls API, API fetches interest plus deals, checks inventory, sorts, and responds. This ensures each layer is modular and scalable.
You covered the core. On to a different problem. Feel free to think out loud as you work through this. The coding problem is now on your screen.
To break it down, first we measure the length of the entire list. Once we know the length, we divide it by the number of parts. Each part will have either the quotient length or that length plus 1 if we have a remainder. We assign more nodes to the first parts if needed. We then walk through the list, breaking links at the right points, and return each segment as a separate list.
You've described the high-level plan. Now walk me through the algorithm on the concrete example head AEGs 1 and 2, 3, 4, 5, 6, 7, 8, 9, 10. K3.
First,
Show me exactly how you compute the sizes and where you break the links.
we start by counting all 10 nodes. We divide 10 by 3, giving 3 each. The remainder is 1, so the first part gets an extra node, 4. Thus, the first part is 4 nodes long, the next 2 parts are 3 nodes each. We traverse, break after the 4th node, then break after 3 more nodes, then after the final 3. This yields lists of 1 through 4, 5 through 7, and 8 through 10.
Moving on, let's see how you do with a different angle. Design a practical Amazon product review system that can collect reviews, detect abuse, and display trustworthy ratings. Cover requirements, APIs, data model, scaling strategy, reliability, and operational trade-offs. Feel free to think out loud as you work through this.
We need requirements. Users submit honest reviews, and we detect fraud. The API would have endpoints to submit reviews, retrieve ratings, and flag abuse. The data model would include review text, ratings, user history, and trust scores. For scaling, we'd use distributed databases and a fraud detection pipeline that runs in real time or batches. For reliability, we'd prioritize review availability, but delay untrusted ones for moderation. Operationally, we trade real-time display of all reviews for trust. We might use machine learning to rank trusted reviews higher.
You mentioned a fraud detection pipeline. Walk me through how you detect abuse. What signals would you use, and at what point in the flow would you flag a review?
We'd analyze behavior patterns. Signals might include rapid submissions, repeated identical text, or low trust from similar users. Each review would be scored. Trusted users have more weight, suspicious actions trigger flags. In flow, we'd collect the review, run it through abuse detection, and if flagged, hold it for moderation. Trusted reviews appear immediately, while flagged ones await human or more complex review.
Sketch the major components for me. What are the main services, and how do requests flow between them?
We'd have a review submission service that takes in user reviews. That service calls a trust engine, which evaluates user history and patterns. If trusted, the review is stored and served by a review database and display service. If suspicious, a moderation queue is triggered. The display service then aggregates trusted reviews and calculates ratings. Thus the flow is submit review, trust check, store or flag, and display trusted ratings.
What does the top-level design look like? Walk me through the key pieces and their responsibilities.
At the top level, you have a review submission service that handles incoming reviews. It passes the review to a trust and abuse detection service. That trust service scores the review based on user history and signals. If trusted, it's stored and served by the review database. If flagged, it's sent to a moderation queue. The review display service aggregates trusted reviews and calculates overall ratings. In short, the submission service collects reviews, the trust service ensures reliability, the database stores them, and the display service provides trustworthy ratings.
Got what I needed. Next problem. Tell me about a time you raised the quality bar through testing, reviews, or maintainability improvements. Use a star-style answer and connect the lesson to an Amazon-scale engineering area such as Amazon Retail Search.
The situation was that we had a critical health monitoring feature, and I noticed inconsistent test coverage. The task was to increase quality and ensure every edge case was covered. The action I took was introducing a structured test plan, writing missing unit tests, and establishing code reviews. The result was higher coverage and fewer bugs in production. The lesson, applied to something like Amazon Retail Search, is that raising the quality bar ensures search relevance, reduces errors, and maintains customer trust at scale.
Your reasoning was sound. Let's change the angle. Explain how queues decouple services and improve reliability. Use an Amazon feature such as checkout as a practical example and discuss one trade-off an engineer should consider. Feel free to think out loud as you work through this.
Queues sit between services so one can send a message and the other can handle it later. This decouples them. If one is slower down, the other isn't blocked. In something like Amazon Checkout, a queue could buffer order events so processing doesn't delay the purchase confirmation. This improves reliability. Orders aren't lost during a spike. But a trade-off is eventual consistency. Customers might see a delay before their order is fully processed. Engineers must balance real-time expectations with system resilience.
That wraps up the session. Your results are being prepared.